All right, folks, you made it. The last video of Unit 2 is on Kepler's third law. So the Kepler's laws of orbital motion are things that we could cover very easily. We'll probably cover one more of them in another unit, but they are ways to describe how planets orbit stars and also how moons orbit planets. And for AP Physics 1, they make a special focus of Kepler's third law, which relates the orbital radius of a planet to its orbital period. So what Kepler found out, poring over a lot of data of planetary motion, is that there's a specific relationship between a planet's orbital radius and its orbital period. So the law says the square of the orbital period of any planet in a circular orbit is proportional to the cube of its distance from the center of the orbit. It's a mouthful, and the proportionality is also kind of crazy. It says that the square of the period is proportional to the cube of the radius. And so remember that period is tau. It's the amount of time it takes for one trip around. And then radius is the center-to-center distance between the center of the orbit and the planet itself. So what we're going to do in this video is going to derive Kepler's third law to show you where it comes from. You might need to do that for an open response question on the AP exam. And then we're also going to focus on that proportionality, which is just a little bit wild. So a lot of the same stuff happens. Gravity is the only force acting on a planet that's in orbit, and we're going to assume that the only force of gravity that matters is the one coming from the sun at the center of the orbit, or near the center of the orbit of that planet. So gravity causes centripetal acceleration. So gravity is the only force, and that causes net centripetal force, which is mv squared over r. Once again, the mass of the satellite cancels. This case is the mass of the planet, whereas big M is the mass of the star. One of the r's can be multiplied away, and we are left with a very similar equation. It's actually the same equation that we saw in the previous video. Okay, now we have an equation that relates orbital speed to orbital radius, and we want an equation that relates orbital period to orbital radius. So way back at the beginning of the unit, we talked about circular motion, where the speed of an object in circular motion is equal to the distance it travels, and we used the circumference of a circle as the distance something travels in a certain amount of time, and if it travels the exact circumference of a circle, the time is equal to the period. So we can use 2 pi r over tau to get that period variable into this equation. All right, so that's really like the major move, and everything else is just algebra after that. But it's important to remember that that v squared, or the 2 pi r over tau, is relevant at any time you have circular motion. Okay, so I put in the equation for speed, and I square it. And then I it kind of blows up the right side, but then things can get organized. So gm over r on the left-hand side, and then 4 pi squared r squared over tau squared. And so again, our goal is to make this relationship between tau and r. So we are going to cross multiply. And so what we get when we cross multiply is we have tau squared times gm, and that's equal to 4 pi squared r cubed. All right, so actually at this point in time you can see the period squared radius cubed relationship, and I just want to like clean this equation up a little bit. So I'm going to divide both sides by gm, and so tau squared equals 4 pi squared over gm times r cubed. So this is the equation for Kepler's third law. Using this equation, you could actually find the orbital period of a satellite if you knew its average orbital radius and the mass of the sun, the star that it was orbiting. So that's that. the last thing I wanted to do was to work with that proportionality. So we're going to compare two planets, planets A and B. Planet A has an orbital radius of r and an orbital period of tau. And planet B has an orbital radius of 4r, and we are going to just wonder what the orbital period is for that planet. So I've dispensed with the writing of the problem, and we're just working with this proportionality. Now, we've done a bunch of problems, examples, where I fill in this whole equation. I'm going to skip that. I know that the only two variables that matter are period and radius. And I can solve this proportionality for period if I take the square root of both sides. So the way that works with exponents, if this is cubed, if I wanted to take the square root of something that's cubed, I would divide this exponent by 2. So the orbital period is proportional to the radius to the 3/2 power. If you prefer writing that differently, it could be the square root of r cubed, and it comes to the same thing. All right, so the orbital period of A is tau. The orbital period of B is what I'm going to find, and so this is going to be the orbital period of B. And that relates to how I would change this orbital radius. Well, it's 4 times the size, and so I need to focus on taking that radius to the 3/2 power. Well, 4 to the 3/2 times r to the 3/2. I have to figure out what 4 to the 3/2 is. This notation is actually really helpful. It's the square root of r cubed. And with exponents, I can do that in any order I want. So I can take the square root of 4 and then take that to the 3rd power. Square root of 4 is 2. 2 to the 3rd power is 2 times 2 times 2, and that is 8. So this proportionality tells me if I change the radius by a factor of 4, I will change the period by a factor of 8. So this orbital period is 8 tau. So 8 times the orbital period if it's 4 times the orbital distance. That is not a doubling relationship, right? If I had 5 times the radius, it'd be 5 to the 3/2 power, which is not equal to 10. So just be mindful of that. And so that is Kepler's third law, and that's the last video of this unit. Thanks.